Hello everyone, we are Team 48.5 from National Institute of Technology, Trichy, participating in TA India Analog Design Contest 2012-13. Our entry for this contest is solar power based intelligent battery charging system compatible with existing home inverters. This video is a demonstration of the working of the system. Our work focuses on solving the power crisis situation that prevails in many parts of the country with solar energy. This is achieved by using solar power to its fullest potential. The commercially available solar chargers stop extracting solar power once the battery is fully charged. However, our system ensures that this unused power is utilized by diverting it to the loads through the inverter. And in this process, the electricity bill is also reduced. This system comprises of two main modules, a charge controller to control the power flow from the solar panel and a power management system to manage the power flow between the DC bus and the load.
Two 80-watt panels are connected in series to implement this system. Let us now look at the individual modules.
This is the charge controller PCB. It is a self-sustained system completely powered by the PV panels and requires no external supply. The charge controller is a buck-type DC-DC converter. This comprises of the IGBT, inductor, input capacitor and output capacitor. The body diode of a MOSFET IRF 540 is used as a fast recovery diode. The gate driver IC UCC 27322 is used for firing the IGBT using the high frequency switching pulses generated by the launch pad. A RCD snubber circuit is used to eliminate transients. The MSP 430 launch pad is used as the main controller. It uses a G2 series microcontroller. Hall effect current sensor LA55P is used to sense current from the PV panels. A differential amplifier circuit constructed using LM358 is used for voltage sensing. The entire board gets its regulated power supply from the LM2575 12-volt switching regulator. Now we will demonstrate the working of the charge controller. A voltage probe is used to measure the voltage and a current clamp measures the current. The power is calculated and displayed in the power analyzer. The output waveforms are observed on the digital storage oscilloscope. As mentioned earlier, the charge controller is completely powered by the PV panels. The charge controller has two modes of operation, the maximum power point tracking mode and the voltage control mode. We will now demonstrate the maximum power point tracking mode. When the circuit is switched on, we can see that the power keeps on increasing and settles around the maximum power point. The maximum power point tracking is implemented using perturb and observe algorithm. These are the voltage, current and power values observed in the digital storage oscilloscope. Because of the algorithm, we can see at steady state the power settles and oscillates above the maximum power point. Next, we will demonstrate the working of voltage control mode in the charge controller. This mode prevents the overcharging of the battery by maintaining the battery voltage constant. A multimeter measures and displays the battery voltage. We can see that the battery voltage increases, but it is prevented from increasing beyond a certain value. The charge controller maintains the battery voltage constant at 14.15 volt. Now let us see how the charge controller fits in the system. The shift from MPPT to VOC mode will be demonstrated. Consider a case when the load is heavy or the battery is insufficiently charged. In this case, the charge controller operates in MPPT mode. This is indicated by the green LED. When there is a sudden decrease in load, the battery voltage begins to rise. When the voltage limit of around 14 volt is reached, it is maintained constant to prevent overcharging. This is the voltage control mode indicated by the blue LED. Voltage control mode operates when the load is light and the battery is sufficiently charged. The shift from VOC back to MPPT mode occurs when there is a sudden increase in load. The charge controller goes back to MPPT mode to extract maximum power from the PV panels. This is the MSP430 experimenter board, which is the main controller for the power flow management system. Let us look at the menu options. The start option initializes the system. This is the clock page which displays the time. It also provides option for changing the time. The battery page indicates the state of charge of the battery. It also tells us if the battery is charging or discharging. This option is used for recalibrating the state of charge of the battery. The power flow option displays the power extracted from the solar panels. This is the power flow management PCB, which is completely powered by the battery already existing in the home inverter system. We shall now look at the individual components. The regulated DC supply is obtained from the adjustable voltage regulator LM317, which is adjusted to give a constant supply of 10 volt. A TLV1117 3.3 volt linear voltage regulator is used to power the MSP430 experimenter board. Hall effect current sensors LA55P are used to sense the currents from the PV panels and the current flowing through the battery. TL084 op amps are used as voltage buffers to couple the current sensor output to the microcontroller. Since the battery current is bidirectional, a level shifter circuit is used to obtain voltage in the proper range so that it can be processed by the microcontroller. TLV1117 1.5 volt voltage regulator provides the voltage reference of 1.5 volt for the level shifter circuit. The battery voltage is sensed using a differential amplifier circuit constructed using op amp TL084. Since the op amps require dual power supply, the switched capacitor voltage converter IC LMC7660 is used. For the switching operations, two relays are used, 10 ampere and 30 ampere rating respectively. Quadruple half-edge driver IC L293D is used to drive the relays from the microcontroller. The state of charge of the battery is calculated by Coulomb counting method. From the graphic display, we can see that the battery is charged by the PV panels. The existing inverter operates in two modes, rectifier mode to charge the battery and inverter mode to supply the AC loads from the battery. The mode of operation of such an inverter is controlled by switching the AC main supply to the inverter using a relay. Thus this controls the power flow. When the state of charge of the battery reaches 80%, the supply is disconnected and the battery is made to supply the loads. Now the battery might discharge depending on the load. We can see the change in indication in the inverter. When the state of charge of the battery decreases to 60%, the mains is connected back to the inverter and hence supplies the loads. We can see the change in indication in the inverter. This is done so that there is sufficient backup even in case of a power failure. By the switching algorithm, PV power is used effectively and power consumption from the grid is reduced. It is observed that this system saves 266 Wh more than the commercial solar chargers in about 4 hours for a constant load of 135 watt. The Coulomb counting method to determine state of charge of the battery cannot be used for long periods of time because of its error accumulating nature. So recalibration of SOC at periodic intervals is required. The system provides option for manual recalibration. In the actual system, recalibration is done automatically. After 1 minute, the voltage value sampled is 12.13 volt. Open circuit voltage extrapolation method is used here. This involves disconnecting the battery from the inverter and sampling the open circuit voltage of the battery at 1 minute and 5 minute intervals. Based on these values, the state of charge of the battery is accurately predicted. The recalibrated SOC is displayed. The analog subsystem consists of the voltage regulation unit, voltage sensors, current sensors with buffers, and power sensing circuit. Because of the non-linearity of the inverter circuitry, the current drawn from the battery and hence the output of the current sensor becomes distorted. Hence, a RC filter is used for signal conditioning. We can see the conditioned signal in the DSO. The gate driver IC UCC27322 amplifies the switching pulses from 3.3 volt to 12 volt. This portable data logger can be used for energy auditing purposes. The data is stored in a micro SD card and can be accessed by plugging it into a computer. We can see the voltage and current values stored in an Excel file. Until now, we saw the working of individual subsystems. This is the complete setup of the system. The charge controller is operating in MPPT mode indicated by the green LED. The control strategy disconnects the mains and hence PV panels and battery together supply the load. Since the input current cannot meet the load demand, the battery discharges. The power sensing circuit LED is on, indicating the presence of power in the AC mains. The portable data logger system continuously stores the values of voltage and currents of the PV panels in the micro SD card.
This system can be readily installed for use with the existing home inverters. This work will definitely contribute in solving the power crisis situation and reduce the electricity bill. We believe this is a small step in moving towards a self-sustainable and clean energy. Thank you.